Hi students, welcome back to this section on basic geometrical ideas. We have discussed these three topics so far. We know that points are nothing but dots, they are denoted by capital letters. We know that a line segment has a starting and ending point, and this is an example of a line segment and it's denoted by AB with a bar on top of it. And we know lines go on indefinitely on both the sides, and this point A and point B, these are 2 points on this line, and you denote it as AB with a bar on top of it, but you have arrows on both the sides of the bar. All right, now let's get to the next topic. We'll try to understand what planes are. All right, now a plane, as we discussed when we discussed parallel lines, a plane is nothing but a flat surface. It's just a flat surface. What's an example? Like now you're seeing this video on a computer screen or on your phone screen, right? So an example of a plane is your screen, your computer screen or your mobile screen is a flat surface, and it's an example of a plane. All right, you can see that planes are two-dimensional in nature. A plane has two dimensions. Say your computer screen, it has a length and a breadth, right? You can see that it has a length and it has a breadth. Similarly, your mobile screen also has a length and it has a breadth, right? So you can see that planes are two-dimensional, or they have two dimensions. What about a line? You can see that a line just goes on like this, right? It's a one-dimensional figure, and we call that one dimension as length. We measure it in terms of length. So a line has only one dimension, a plane has two dimensions. Now let's take an example of a plane. Your table over here, where you're sitting to study, you can see that your table is also a plane and it is a flat surface, right? It has a length and a breadth. This is a flat surface, it is a two-dimensional surface. Now draw a line on the floor and on your table. You can see that they won't intersect, like we discussed before. They never intersect because they are not on the same plane, right? They won't intersect, but because they are not on the same plane, you cannot call that these two lines are parallel. Okay, so for two lines to be parallel, they need to be on the same plane, and we have seen that planes are two-dimensional. They have length and breadth, and a plane is nothing but a flat surface. All right, let's get back to our topic list. So we have got ourselves familiar with these four terms so far. The next term that we want to analyze is a ray. What is a ray in geometry? Let's try to understand. Now, a ray can be understood as a portion of a line. It's just one part of a line. Say for example, this is a ray. Now you can see that it has a clear starting point, and you can see that it does not have an ending point. It goes on endlessly in a direction, right? It goes on endlessly in a direction. So this type of a geometrical figure is what we call a ray. Now can you think of some applications where we can describe the thing as a ray? Yeah, take a torch for example. You have a torch. This is a torch. Okay, imagine this is a torch. Now you can see that the light from the torch is going like this, right? These are all rays. Now what do we call the rays from the sun? We call them sun rays, right? They're also rays. You have the sun over here. They have a clear starting point, that is the sun, and they go on endlessly, so we call them as sun rays. So these type of geometrical figures are what we call as rays. All right, now let's mark 2 points on this ray. I mark the starting point as point A, and this point over here which is on this ray, I mark it as point B. All right, now how do we name this ray? We have seen how to name a point. We have seen how to name a line segment. For example, this is a line segment AB. We have seen that to name a line AB we use this notation. Now to name this ray AP, we call this as AP with a bar, and this arrow is only on one side. That's why we imagine it as a portion of a line. Like if this was to be converted to a line, it has to extend in both the directions. I'd have to extend this a little bit over here and draw an arrow like this, right, to make this into line AP. Now we are not considering this part, we are only considering this portion of the line. That's why we call it a ray, and we mark it and we denote it like this. All right, you can see that the point A over here is the starting point, and the point P is a point on the path of the ray. Right, now an interesting thing, let's try to analyze this a little bit more. Let me take one more point on this ray. Okay, so this point over here, this point B, is also on the ray. Now you can see that I could name this ray either as AP or AB. Both denote the same ray, right? Because it goes endlessly. Even if I only have drawn the ray till B, A and B, if I extend it, and finally I will reach point P, right? Imagine this is on top of the ray, right? Just to analyze it, I'm drawing it over here. Now therefore we can say ray AP and ray AB are the same ray. It's not different rays, it's the same ray. But you also should know that you cannot call ray AP as ray PA. This would be wrong. Okay, you cannot call it like this. That's wrong. Why? Over here you need to have the starting point, and in the case of this ray, what is the starting point? It's A, right? A is the starting point. Therefore you cannot call it PA, it has to be called AP, and also you can call it AB because B is another point on the ray. All right, now we know what a ray is. Let's try to do a question. We have two true and false questions, and the figure is given over here. Let's read the question. A is a point on ray OB. Okay, that, and we have to state whether the statement is true or false. Now what is ray OB? What is the starting point of ray OB? It's over here, right? O is the starting point of ray OB, right? Ray OB is nothing but OB with a bar on top of it. The starting point of ray OB is O, and it goes on like this on one side. Now where is A? A is over here, and you'll see that A is not on OB, right? A is not on OB. Therefore this statement over here is false, right? Did you get that? OB is only, ray OB is only this part. Starting from O, it just goes on like this. This is OB. A is not on OB. All right, now the next question is, OA and OB are different rays. What do you think? OA is this ray over here, which starts at O and goes on endlessly towards the left, right? And OB is the one over here. It starts over here and it goes to the right endlessly. So clearly these two are different rays. Imagine whatever I'm drawing is on top of this figure. Okay, I'm just drawing it down so that we are able to analyze it. And therefore we have seen that OA and OB are different rays. They're going in different directions. It's just that they have the same starting point. Therefore this statement over here is true. All right, let's get back to our topic list. We know what rays are, and we have seen how we name them. Say you have AB and you have a line on top of it and a bar only in the direction of B. So this means this is a ray of type like this. You have A over here, which is the starting point, and B is one point on this ray in the path of the ray, and we call this as ray AB. All right, now the next topic that we are going to discuss is curves. Let's see what we mean with curve in maths. All right, now a curve describes the path of a continuously moving point. That's what we know what a point is. Imagine a point is continuously moving, like you have the point over here. Say I start over here and it just keeps continuously moving. This could be called a curve. All right, now let's draw a few curves. So I could draw it like this, like this, like this. These are all curves, right? They are all paths of continuously moving points. Now you can note over here you have a straight line as well. Now a curve in maths can be straight as well. In common usage we don't call a straight line as a curve, but in maths even a straight line is a curve, because a straight line is also the path of a continuously moving point. Like you have the point over here, if the point keeps going on like this, you get a straight line, and that also is a curve. So all of these are curves. If you doodle anything on your paper, you will get a curve. Just make a continuously moving point, a path of a point, and you will get a curve. All right, now let's try to go deeper. Let's try to understand the different types of curves. If I have a term that says simple curve, What do I mean with that? Simple curve means it does not cross itself. If a curve does not cross itself, we call that curve a simple curve. What do I mean with that? Like, if you have a curve is going on like this, and over here if it goes like this, you can see at this point it's crossing, right? In this section it's crossing itself. This is also part of the curve, and this part is crossing this part of the curve. So you will say that this type of a curve is not a simple curve because it's crossing itself. All right, now we have these curves which we drew before. Let's try to analyze each one and say whether it's a simple curve or not. All right, let's start with the first one. Does this curve cross itself? No, it does not, right? You can find no section where it crosses itself. So yes, this is a simple curve. What about the next one? Over here, you can see over here it crosses itself. Therefore, this curve is not a simple curve. It's not a simple curve. What about this one? No, it does not cross. Even though it meets over here, it does not cross itself anywhere, right? So yes, this is also a simple curve. What about this one? Yes, over here it crosses itself, and over here you can see it crosses itself. Therefore, this curve over here is not a simple curve, right? And what about this straight line, which is also a curve in maths? It does not cross itself. So yes, that is also a simple curve. All right. Now let's look at these two curves. This one over here, you can see it is not closed. So we call this one an open curve, and over here you can see it's closed. So this is a closed curve. Like for example, if you catch a fly and you keep it inside here, you can see the fly can go out over here, right? Through this way. That's why it's open. It's like an open jar. So it's open. If you have the fly inside here, it cannot go out, right? It'll hit the boundary over here. It cannot go out, and this type of a figure is called a closed curve. All right, let's quickly revise. What all did we learn? We learned that a curve is nothing but the path of a continuously moving point. All right, we saw that curves can be straight in maths. That's the second point we learned. And we learned what simple curves are. Curves that don't cross each other are simple curves. We learned about open curves and closed curves. If this type of a figure, you see that this point is not meeting over here, so it's open. This is an open curve. This is a closed curve. All right, let's get on. Say you are an agriculturalist and you have this field of land. Okay, now let's take 3 points. I take 1 point over here, one over here, and one over here. So I can see point A is over here, it's inside the land. Point B is on the boundary, and point C is outside the land, right? Let's try to analyze these 3 points. I write the 3 points over here. Where is A? A is on the interior or the inside of the curve, right? This is a curve, right? And you can see it's a simple curve. Yes, and it is a closed curve, right? It's closed. It's simple because it does not cross itself, and it is a curve because it's the movement, the continuous movement of a point. Now point A you can see is inside the curve. Point B you can see is on the boundary of the curve. Okay, and point C you can see is on the exterior of the curve. All right, this is just an interesting property. You may be given a shape and a few points, and you may be asked to say whether each point is in the interior, the exterior, or on the curve. All right, now there's one more term that we try to analyze over here. If I take this much, that is the interior plus the boundary, we call that the region of the curve. So this yellow area is the interior plus the boundary, and that is in the region of the curve. So I can say point A and point B are on the region of the curve, right? Right. I can say point C is not on the region of the curve. All right. Now let's do a few questions. The first question says draw an open curve with only line segments. So you can only use line segments. You cannot use a curve like this is a curve. You cannot say if you drew it like this is an open curve because this part is open, but we are using curves also, right? So try to pause this video and try to draw it on your own. All right, now you can draw it like this, right? This is an open curve because these 2 points don't meet each other, and you have only used line segments. So all right, so this we have done this question. Let's try to do the second one. Draw a closed curve with no line segment. So it has to be closed. So if you have a figure like this, it's closed, right? Because these 2 points are meeting, so it's closed, but you should not use any line segments. All right, pause the video, try to do it on your own. All right, we are back. You can draw it like this, right? Or you could draw a circle. This is a closed curve and it does not have any line segments. All right, so let's get back to our topic list. We have covered what curves are, we have seen what simple curves are, and we have seen what closed and open curves are. All right, now the next topic that we'll be discussing is polygons. Let's dive in. What do we call with polygon? Now in Greek, the word polygon has two parts. You can see it has poly and it has gon. So poly means multiple and gon stands for angles. So in Greek, this actually literally means multiple angles. So figures with multiple angles is what we call polygons. Let's try to see a few defining parts of a polygon, and with that analyze what polygons are. Now polygons are simple closed figures, okay, and they are only made up of line segments. This type of figures are called polygons. Let's try to understand what are the terms that we have used and what is the meaning of that. We have seen that polygons have to be simple. What do we mean with a simple curve? A curve that does not cross itself. So if you have a figure like this is not a polygon because it's crossing itself, right? Polygons have to be simple figures. Now they have to be closed figures. What does that mean? If you have an open curve, this is not a polygon because it's not closed, right? We have seen open curves and closed curves. So polygons by definition have to be closed. All right, now what is the next thing? They are made up of only line segments. So these are the three necessary conditions for polygons. Let's take an example. Say you have this one over here, this figure over here. You can see that this figure is simple. It does not cross itself, right? So this part is satisfied. It's closed. It's not open, it's closed. You can see it's closed, and it is only made up of line segments. Therefore, yes, this is a polygon. Now, using this definition, let's try to analyze certain figures and identify whether yes, they are a polygon or no, they are not a polygon. Now, before we do that, also remember that the points of this polygon have to be in the same plane, right? If you draw these 4 points which you have joined to make this polygon on your table, and this point if you draw it on the ground, okay, then if you join all the points together, you will still get a simple closed figure, and it's only made up of line segments. But that is not a polygon because all the points should be on the same plane for a polygon, okay? So that would be a 3-dimensional figure, and currently in this section we are only dealing with 2-dimensional geometry. We will learn more about 3-dimensional geometry soon, but remember, for a polygon all the points, okay, should be on the same plane. You cannot have one point on the floor and these 4 points on the flat surface of your table. And if you join all those points, the figure that you get is still simple and closed and only made up of line segments, but that is not a polygon because the points have to be on the same plane. All right, now keep that in mind. We'll revisit it when we think of three-dimensional geometry. I'm just putting in the seeds in your mind so that you can connect with them when we come to 3-dimensional geometry later. All right, now let's have a few figures over here. We'll try to identify whether each of these are polygons or not, and remember, all of these are 2-dimensional figures for now. All right, now the first one, is it made up of only line segments? Yes, so this condition is satisfied. Is it a simple curve? Yes, it does not cross itself, right? And is it closed? Yes, it's closed. So I can say yes, this is a polygon. All right, what about this one? Is it simple? Yes, it does not cross itself, right? Is it closed? Yes, you can see it's closed, it's not open. And is it only made up of line segments? Yeah, you don't have anything else. This is a line segment, this is a line segment, this, and this. All of these are line segments. So I can say yes, this is also a polygon. Now the next one, pause the video and try to do it on your own. Okay, so you can see that this one over here is not made up of only line segments. Here you have a curve, and this is not a line segment, this is a curve over here. Now this is simple because it does not cross itself, it's closed, but it is not made up of only line segments. Yes, you agree, I agree that a curve is also, a line is also a curve, but every curve is not a line, and this type of a curve is not a straight line, and hence it's not made up of only line segments. So this condition is broken, so this one is not a polygon. So remember, this is not a polygon. All right, what about this one? This is simple, it does not cross itself, but you'll see it's not closed, right? It's open over here, and hence this is also not a polygon. All right, what about a circle? If you take a circle, you'll see that it's simple, it's closed, but it's not made up of only line segments, so this also is not a polygon. All right, let's go on. Now let's try to make some simple polygons with 5 lines, 4 lines, 3 lines, and 2 lines. Okay, these are segments, line segments. Let me write it as segments. We'll use 5 line segments, 4 line segments, 3 line segments, and 2 line segments to form polygons. Let's try to do that. Try to form the polygon with 5 line segments. Okay, you can draw it like this, right? This is the one that we have seen before also. You can see that it has 1, 2, 3, 4, and 5 line segments, right? And this type of a polygon is named pentagon. Okay, pentagon. All right, now what about the case where you use 4 line segments? That's like this. It has 1, 2, 3, and 4 line segments, and this type of a polygon is what we call a quadrilateral. Now this is a generic term. Some of you might know that this is a rectangle also. So rectangle is a particular type of quadrilateral, but any 4-sided polygon that you can form, say for example this one is not a rectangle, but this is a quadrilateral. So any polygon that you can form with 4 line segments is called a quadrilateral. All right, now let's form a polygon with 3 line segments. So that would look like this, right? I have 1, 2, and 3 line segments in this figure, and this is what we call a triangle. Okay, now try to pause this video and form a polygon with 2 line segments. All right, you'll have seen that you cannot do that, and that's because you need a minimum of 3 line segments to form a closed figure, right? You have 2 line segments, you draw one like this, you draw one like this part is open, right? And we have seen that polygons are simple closed figures, so it has to be closed. To close this section you need at least 3 line segments, and if you use 3 line segments we call it a triangle. So you can see that with 2 line segments you cannot form a polygon. So the polygon with the minimum number of line segments is a triangle, and it has 3 line segments. All right, let's go on. Now let's try to name this polygon. Okay, so I have the polygon over here. Let me identify the edges of this polygon. All right, these are the edges, and I name them as A, B, C, D, and E. And now I can call this polygon as polygon ABCDE. It's ABCDE. See, note the corners are named in order. You have A, then B, C, D, and E. You cannot call this polygon as polygon ACBDE. The points are still the same. It's A, C, B, D, E. But when you name them, you need to start at one point and go either side in the clockwise or in the counterclockwise direction. So I could call this polygon as I start at A and going this direction, I have A, B, C, D, E. That's how I get this name. Another way is I could go this direction. So then the same polygon could be called polygon A, E, D, C, B. That is also correct. Or you can start at point B. If you start at point B and go in this direction, you can call this polygon as B, C, D, E, A. This is polygon B, C, D, E, A. This is also correct. Or you could go start at B and go in this direction. In that case, it would be called polygon B, A, E, D, C, right? In all these cases, you can see that the corners are put in order when you name the polygon. You cannot call this, if you call this as polygon B, D, C, E, A, this is wrong because the corners are not in order in this case. And to name a polygon, you have to maintain the corners in order. All right. Now, let's try to analyze these 5 terminologies for polygons. I have a polygon over here. Let me mark the edges as A, B, C, D, E. And now we start with sides. These are important terminologies which we will be using in problems and to go deeper into geometry. So make sure you write all of these in your notebook. Maintain a well written notebook so that you can easily revise all these topics just before the exam. Alright, now let's start with sides. Sides are nothing but line segments forming the polygon. It's line segments forming the polygon. So can you write all the line segments that are used to form this polygon? Pause this video and try to do it on your own. Alright, so you can see these are the 5 line segments used to form this polygon. You have AB, you have BC, you have CD, you have DE, and you have EA. And these are the 5 line segments used to form this polygon. Now let's try to understand what a vertex is and what the vertices are. So the vertex, the plural of vertex is vertices. Okay, vertex is singular, vertices is plural. All right, now with vertex you mean the meeting point of the sides. Say you take these two sides AE and AB, they meet at point A, right? So A is a vertex. Or similarly B, AB and BC meet at B, so B is a vertex. So all these edges are vertices because the plural of vertex is vertices, the singular is vertex. All right, now let's go on. Let's see what are adjacent sides. Adjacent sides are two sides with a common endpoint. Two sides with a common endpoint. Say you take A, B and BC, this one and this one. You can see that these two sides have a common endpoint, that is B. B is a common endpoint of AB and BC. Therefore, we can say line segment AB and line segment BC are adjacent sides. Alright, now let's go on to the next one, adjacent vertices. Adjacent vertices are endpoints of the same side. Say you take AB, you take this side AB, what are its endpoints? You have point A and you have point B. That's why A and B are called adjacent vertices. Or you take DC, in this side DC, point D and point C are adjacent vertices, or vertex D and vertex C are adjacent because they are the endpoints of the same side. Alright, now let's see what diagonals are. If you join non-adjacent vertices, you get the diagonals. So you have to join non-adjacent vertices. Say you take this point. What are the adjacent vertices of point A? E is an adjacent vertex and B is an adjacent vertex. So you can join A to D, you will get a diagonal. If you join A to C, you will get another diagonal. So let's draw all the diagonals. So you can see these are all the diagonals and it's by joining non-adjacent vertices. Let's write the diagonals. So I have AD, I have AC, I have EB, I have EC and I have DB. These are the 5 diagonals of this pentagon. And we have seen 5-sided polygon is called a pentagon. These are the 5 diagonals of this pentagon. Alright, now you will notice that if you join adjacent vertices, you won't get a diagonal. Like if you join A and E, these are adjacent vertices, right? What are adjacent vertices? Endpoints of the same side. So AE is the same side. So A and E are adjacent vertices. If you join A and E, you won't get a diagonal. Alright, now we have got a good idea about polygons. Let's try to do a few questions. Okay, this question says, what is the number of diagonals of a triangle? Alright, let's draw a triangle. We know a triangle is a 3-sided polygon, right? So we have a triangle over here. Now the question says, what is the number of diagonals of the triangle? We have seen to get a diagonal, we have to join non-adjacent vertices. Now let me take a vertex. Over here, say this is vertex A. And let me mark this as B and this is C. can you tell me out of B and C which is non-adjacent to A? You will find that both are adjacent. So A does not have a non-adjacent vertex, right? Because if you take side AB, A and B are adjacent vertices. If you take side AC, A and C are adjacent vertices. So you can see that for a triangle, you have zero diagonals. You cannot draw a diagonal for a triangle. What if it was a quadrilateral? If it was a quadrilateral, you could have drawn 1 and 2. You could have drawn 2 diagonals. This should be a straight line, okay? You could have drawn 2 diagonals. But for a triangle, you can not draw any diagonal. Alright, let's do the next question. What is the number of diagonals in a hexagon? Now, we have seen that if you have 3 sides, it's a triangle, right? If you have 4 sides, it's a quadrilateral. If you have 5 sides, it's a pentagon. And if it has 6 sides, it's called a hexagon. So, we are asked to find the number of diagonals of a 6-sided figure. Now pause this video, draw a 6-sided figure and try to do it on your own. Alright, now let me draw a hexagon over here. So it has 1, 2, 3, 4, 5, 6 line segments, right? Now let me start from this vertex over here. You remember a diagonal is obtained by joining non-adjacent vertices. Alright, so if I take this one over here, can I say this one is non-adjacent? No, because in this side these two are endpoints. Can I say this one is non-adjacent? Yes, it's not. These two are not endpoints of a side. What about this one? Yes, these two are non-adjacent. What about this vertex? Yes, these two vertices are non-adjacent. What about this vertex? No, these two are adjacent vertices. Alright, now to get diagonals, I just need to join these, right? So I have got 3 diagonals. Similarly, let me join this vertex over here with its non-adjacent vertices. So I can draw it over here, and over here. These two are adjacent to this vertex, right? Alright, so I have 3 more. What about, let me just name them so that I can easily address them. What about vertex C? Vertex C, I can see that already I have joined C and A. What are the other two? I can join C and F, and I can join C and E, right? I get 2 more diagonals by joining. C and F are non-adjacent vertices. C and E are also non-adjacent vertices, and C and A is already joined in yellow. Alright, now let me go to vertex D. What are the points with which I can join D? Remember, I am trying to join non-adjacent vertices. So I can join D and F, right? D and B and D and A are already joined. So I can join D and F. Now with E already I have joined C, B and A, and with F already I have joined B, C and D. So I've drawn all the possible diagonals of this hexagon. Now how many are there? We need to count them. I have 3 over here. I have 3 in blue. I have 2 in green and 1 in orange. So I can see 3 plus 3 is 6, plus 2 is 8, plus 1 is 9, and I have a total of 9 diagonals in this hexagon. In future classes, we will learn about methods by which these type of things can be identified without counting. But at this level, we try to draw the figure, try to draw the diagonals and count them and find the answer. Let's get back to our topic list. Alright, so we have covered these 7 topics so far. We have seen that polygons are simple closed curves made up of entirely line segments, and all the vertices of the polygon have to be in the same plane. So we have learned that, and we have seen what diagonals are, we have seen what sides are, what adjacent sides are, what adjacent vertices are, and what vertices are.